topic is impulse and momentum. In the first section, 5.1, I'm going to talk exclusively about the term impulse. Although impulse is very, very much related to change momentum, they are in fact equivalent. In this section, I'm going to talk exclusively about impulse, and then in later sections, I will be talking about the relationship between impulse and change in momentum. I'd like you to make sure that in beginning this topic, impulse and momentum, that you download the WS, the worksheets for this topic. What you're going to find on the first page is a list of all the vocabulary that pertains to the topic. So we'll really only be going over a few of those vocabulary words in this section, but if you have all the vocabulary on hand, it'll give you an overview of what we're going to be discussing for the entire topic. All right, now the word collision. A collision is an event in which two or more bodies exert forces on each other for a relatively short period of time. Now, the word collision does not imply anything about the magnitude of the force involved in the collision, or I should say the magnitude of the forces involved in the collision. A collision could be as light as a bird brushing against a leaf as it tries to land on a branch on a tree, or two tractor trailers crashing together. They're both collisions. A collision could be between two galaxies in the universe. All right, so a collision does not imply that there has to be a lot of force. Now, an impulsive force, on the other hand, is a very large force that is exerted over a short period of time. This is relative. I should say a relatively large force exerted over a relatively short period of time. Now, examples of an impulsive force would be, for example, a hammer coming down on the head of a nail, or a foot kicking a soccer ball. Those would be examples of impulsive forces. Now, if I were going to show you an example of a foot kicking a soccer ball, it would be difficult because the best way to show what really happens would be to make the movie of the foot kicking the soccer ball and then to watch it in slow motion, frame by frame. Because what you would see, right, and this would be an example of an impulsive force, a foot kicking a soccer ball would be an example of an impulsive force. And what you would see is that if my hand, my fist here, were the foot, and this balloon were the soccer ball, what you would actually see, slow motion, frame by frame, is that the foot, now, as the foot gets close to the ball, there's no force yet. This would be a contact force. The foot has to be touching the soccer ball in order for the force to start. Now, what I will do is start a graph of the magnitude of the force versus time, because what happens is that as the foot kicks the ball, the magnitude of the force changes. So here's the force, that would be in newtons, and here's the time. That would be in milliseconds, actually. All right? So now, as the foot is getting close to the ball, there's no force. The force is zero until the foot just starts to touch the ball. All right? So there's the force is zero until it just starts to touch the ball. So right at about this point here is where the foot first makes contact with the soccer ball. And what happens is that the soccer ball deforms. This word. The soccer ball deforms. All right? It has some elasticity to it, so it squishes. Right? And as it squishes more and more, the force increases. So what happens, all right, is that we get some static electricity here. My hair is sticking to the balloon. So the force is the force is zero. It makes contact. The force is very, very small, but the force increases as the foot kicks into the soccer ball and the soccer ball deforms until it reaches some maximum force, right? When it's as far pushed into the soccer ball as it's going to get. All right, so let's draw that on the graph. The force increases to some maximum point. Let's say that's the maximum. Then what starts to happen is as the ball starts to regain its original shape, it's elastic, so it bounces off the foot and it starts to regain its original shape. It's going back to its original shape because it is elastic. And there's a point at which the force is back to a minimum, and then the ball is either rolling across the ground or it sails up into the air. It's been kicked up into the air. In any case, there is no longer a force. The force is zero because the ball and the foot are no longer in contact. So what happens is the force decreases again back down to zero. And this makes a nice symmetric curve, all right? And what you find is that the area under this curve, all right, the area under this curve, which we know from previous sections is the force times the time, all right? The force times the time, the area under this curve is the impulse. And the symbol for impulse is the capital letter J. Now, the greater the force, or the longer the time that the force acts, the greater the impulse. A force acts over a period of time. A force acts over a period of time. Here's a fun little example of how the same force acting over a longer interval of time results in a greater impulse on an object. The same force, but if you increase the amount of time, then there's a greater impulse. Let's see how that works with a blowgun here. All right, this is a piece of half-inch PVC that you get from the hardware store. Now, if I blow in one end, all right, my maximum breath is going to be about the same both times. If I blow as hard as I can twice, the force that I put with my air is going to be about the same. Now, if I load a little paper ball in this end, right, and I blow, right, as hard as I can, well, it didn't go very far. It landed about maybe, I would say that's about 4 feet from the end of my blowgun. Now, what if on the other hand, right, let me go get my little paper ball. I'll be right back. What if, on the other hand, I load the paper ball in this end so that my breath pushes it from here to here instead of just out the end. So the force of my breath is acting from here to here, which is going to take much more time. All right? Let's see how far it goes this time. I'm going to try to use the same amount of breath, all right? My maximum breath here, all right? Wow. Okay. That time, the little paper ball landed, I would say, about 22 feet away. I hope you believe me. In any case, well, you could try this yourself. In any case, what's happening here is basically the difference between a handgun and a rifle. All right, let's look at that in a quick little drawing so that you understand that both force and time contribute to J, impulse. All right? If you have a handgun, the barrel of the handgun, all right, let's say the barrel of the handgun, all right, is about this long, okay? So the bullet, all right, we'll put the bullet in blue, all right, the bullet is subjected to the force of the exploding gases inside the handgun for this amount of time, from here to here. All right, so that's going to be a small interval of time. All right, this time is small. So the speed of the bullet coming out of the handgun is not going to be very, very fast. I mean, it's going to be fast. But, on the other hand, if you have a bullet going through a rifle, and the rifle barrel is, a little longer than that, probably about that long. Right? The rifle barrel is this long compared to the barrel of the handgun. Then the bullet is being pushed, right? The force of the exploding gases that push the bullet out of the barrel is acting for a much, much longer amount of time. This is time large. All right, that's more time. Less time, more time. So this is one of the reasons why a bullet coming out of a rifle is much, much faster. Here it is coming out. Right? A bullet coming out of a rifle is much, much faster than a bullet coming out of a handgun. If everything else is the same, if the explosion in the handgun and the explosion in the rifle produce approximately the same force, and the masses of the two bullets are approximately the same, then the fact that this bullet is being pushed for a small amount of time, while this bullet is being pushed for a large amount of time, means that this bullet from the rifle is going to be coming out much, much faster than the bullet comes out of the handgun in general. And again, I will be showing you in a later video how more impulse is going to result in a larger velocity. We'll save that for a later video. For now, all right, if the forces are the same, then more time. If the same force acts for more time, then you're going to have a greater impulse. And somehow, again, in a later video, that's going to translate into more speed for the object. Before we go too much further, let's take a quick look at the equation, the symbol, and the unit for impulse. The equation, all right, one of the equations, I should say. Impulse is equal to force times time. Now, J is the symbol for impulse, just like capital F is the symbol for force, and a lowercase t is the symbol for time. Now, what about the unit for impulse? Well, you can figure out any unit by taking any equation for that quantity. Now, here's an equation for impulse, force times time, and putting the correct units for force and time. That will give you the correct unit for impulse. So, the unit for force is the Newton. The unit for time is the second. So what you have is Newton times second. That is that unit is a Newton second. They're multiplied. You might see it Newton times second. That's fine. You might see instead of a dash, you might see Newton times second. That's fine. All right. Now keep in mind that something that would be wrong, if you put Newton per second, that's wrong. It's not force divided by time. It's not Newton divided by second. That would be wrong. It's not Newton per second. It's Newton second. So just say the unit for impulse is the Newton second. Okay, so get rid of that. That's not correct. All right, here's the symbol for impulse, capital J. The unit for impulse is the Newton second. We're going to do 3 very, very straightforward impulse problems just to get started. Here we have an impulse problem. A bat applies an average force, and don't worry about the phrase average force. I'll be showing you the graph again in a little while, and you'll see why we use the average force of 500 newtons to the right to a baseball for 10 milliseconds. That's 10 milliseconds. Calculate the impulse imparted to the ball. Well, the first thing you have to do, since Newton has the unit second inside of it, in other words, the unit second is part of the unit for Newton, you can't mix milliseconds with newtons. We're going to have to convert milliseconds to seconds. So let's do that right away first. All right, 10 milliseconds. We use the factor label method. We want to get rid of the milliseconds. We want seconds. All right, one big giant second is equal to 1,000 little bitty milliseconds. All right, and that's going to be equal to 10 divided by 1,000. We're going to move the place 1, 2, 3 places over. So that's going to be equal to 0.01 seconds. All right, so what we can start doing now, all right, is write our givens. All right, what were we given in the problem? We're given a force of 500 newtons. So F equals 500 newtons. We were given a time of 0.01 seconds. Let's get that over here. All right, the time is 0.01 seconds. They're asking us to find, what are they asking us to find? They're asking us to find the impulse. That would be J. J equals how many Newton seconds? When we get the answer, we'll put it right there. So since we have Ft and we're looking for J, the formula that we decide to use is J equals F times T. All right, so we start plugging in. All right, F is 500 newtons. Time is 0.01 seconds. All right, we multiply that. All right, 500 times 0.01. All right, and what we get, J is 5, all right, Newton seconds. Newtons times seconds. All right, so that's the first of our impulse problems. Since I neglected to give the direction in that answer, this would be a good time to let you know that impulse is a vector. So unless the problem is just asking for the magnitude, 5.00 Newton seconds would be the magnitude of the impulse. If they just say they want the impulse, that means the magnitude and the direction. In that problem, if you go back and look at the problem, it said that the force was imparted to the right, so that means that the impulse here is Newton seconds to the right. All right, again, impulse is a vector, so this is the magnitude of the answer, and this, to the right, is the direction of the answer. All right, remember, if the problem is talking about left and right, then if it's a vector in the answer, give left or right. If the problem is talking about north, south, east, and west, then in your answer, you're going to state whether the answer is to the north, to the south, to the east, or to the west. Whatever convention the problem starts with, you continue with that same convention. Here's our next impulse problem. A hammer applies an impulse of 30 Newton seconds down on a nail in 20 milliseconds. Calculate the average force on the nail during this time interval. All right, again, let's first convert milliseconds to seconds. So, 20 milliseconds. All right, I have milliseconds up on top here. I put milliseconds on the bottom because I want to get rid of milliseconds. I want them to cancel. I want seconds. All right, now top and bottom have to equal each other, and one big giant second is equal to 1,000 little bitty milliseconds. So we're taking 20 and dividing it by 1,000. There's 20 divided by 1,000, 1, 2, 3 places to the left. All right, so the answer is 0.0200 seconds. We've got 3 significant figures there. Okay, so we've got 0.0200 seconds. All right, let's make a list of what we have been given in this problem. A hammer applies an impulse of 30 newton seconds. So we've been given J. The impulse is 30 newton seconds on a nail for 20 milliseconds. So the time is 0.0200 seconds. Now, what are they asking us to find? They're asking us to find the force, right? Given, find, okay, so the force, or even the average force, that's not an issue, all right? The average force is going to be what we're trying to find in newtons, okay, right there. All right, so the formula. Now, we need the correct version of the formula. If we start with J equals Ft, that's fine, but we're not trying to find J, so let's get F by itself. Let's divide both sides by T. Those cancel. F equals J over T is the equation, the version of the equation we will use here. All right, F equals J over T. Okay? I tell you what, I'm going to move it over here so we can go straight across with the answer. All right, F equals J over T. All right, so the impulse, J, is 30 newton seconds. Let me just erase that so it's not in the way. The time, 0.02 seconds. We do the math, right? 30 divided by 0.02, and we get 1,500 newtons. All right, now, that's down. If the impulse is down, then that net force there, that average force there, is down. So we'll say 1,500 newtons down. Oops, running out of the frame here. 1,500 newtons down. All right, so that's the magnitude, 1,500 newtons, and the direction is down. Again, force is a vector, impulse is a vector. Right, you should indicate the direction unless the question asks for only the magnitude. And here's our last simple problem concerning impulse. The gases from a gun going off push a bullet down the barrel. Remember, we were talking about that before with the piece of PVC piping. They push the bullet down the barrel with an average force of 20,000 newtons, resulting in an impulse of 60 newton seconds. How long is the bullet accelerating inside the barrel? All right, so let's make a list of our givens. Okay, what have we been given here? Well, we've got a force of 20,000 newtons. So F equals 20,000 newtons. We have an impulse of 60 newton seconds. So J equals 60.0 newton seconds. They want to know the time. They want to know how long. So what are we supposed to find? We're supposed to find time. The time, and we're going to get the answer in seconds. All right, maybe we can convert that to milliseconds when we're done. Okay, so the formula is going to be J equals F times T. Again, we'll start with that formula. But since we're trying to find time, let's get the time by itself. All right, now, let's erase this. Okay, so copy that down. Pause the video if you have to. Copy that down, because I'm going to erase it so I can fit the formula. All right? All right, so the formula for finding time, well, if J is F times T, right, then T, get T by itself, right, the F's cancel, so T is going to be equal to J divided by F. I'm going to move that up, and we're going to start plugging in, all right? Time is equal to J impulse divided by force. The impulse is 60 Newton seconds. Put that on top, 60 Newton seconds. The force is 20,000, all right, newtons. And when the newtons are going to cancel, right, we're going to get seconds. 60 divided by 20,000, 0.003 seconds, the time. Now, that would be 3 milliseconds. All right, to convert seconds to milliseconds, you're going to multiply by 1,000. So that would be 1, 2, 3 jumps, or 3 milliseconds. You can leave it in seconds. There's really no reason to convert it to milliseconds unless they ask you to. At this time, I'm going to suggest that you pause the video for 6 minutes. You're going to do 3 impulse problems, just like the 3 you just did.